Hello students. So the purpose of this set of notes is to explore the logarithm laws. So these are a set of algebraic laws which logarithms follow. We'll use these whenever we want to simplify logarithmic expressions, which we'll need to do with some frequency whenever we want to, say, solve a logarithmic equation. An important part of solving an equation is simplifying. So let's go ahead and get started. So the first is a rule that you already know. Any logarithm of 1 is 0. And why is that true? So I'm going to jump from here all the way down to there. So the reason that that result is true is because b to the 0 for any base is always equal to 1. Throughout this, I'll assume that I'm working with a valid base. That is, I'll assume that b is bigger than 0 and b is not equal to 1. So log base b of 1 is always 0. The next rules that I'll try to explore is what is the log of a product. If I see multiplication inside of a logarithm, what does that become? And if I can work with multiplication, chances are I can work with division, so I can figure out what the log of a quotient is. If I understand multiplication, well, exponentiation is kind of just iterated multiplication, so I should be able to figure out the log of a power. So let's get started. So I'll fill in these rules as we figure out what they should be, as we prove them. So let's start. So let's try to figure out what the log base b of x times y is. It'll be something in terms of the log of x and the log of y. So what will I do? I'll give those two things name. I'll call the log base b of x, capital X. I'll call the log base b of y, capital Y. So all I've done right there is I've given these things names. That's all I've done. But that's really useful a lot of the time. In this case, it's really useful because this fact, even though it looks like I've just made up a new variable and that doesn't add any information, it lets me perform manipulations. This expression is an expression which is in log form. So since that's in log form, I can rewrite it in exponential form, giving me little x is equal to b to the power big X. And you know what? Let's just, for emphasis, there. I'll draw crossbars on my capital X's to distinguish them. Similarly, this is an equation in log form, so I can rewrite it in exponential form as y is equal to b to the power big Y. So I'll do the same thing. I'll draw some crossbars on my capital Y. Y is equal to b to the power big Y. So that means x times y, and there's a good reason to think about x times y because I want to know the log of x times y, is equal to, well, let's write it down. X is b to the power big X. Little y is b to the power big Y. And, well, that's a product of exponentials. I know a rule for the product of exponentials. In fact, I'll fill it in above. The product of exponentials is given by b to the x times b to the y is equal to b to the x plus y. So down here, I see a product of two exponentials, so I can write it as a single exponential with that thing in the sum. That's b to the x plus big Y. And now I'll just write down the conclusion. I know that this is equal to this. So let's just write that down. So that gives me x times y is equal to b to the power big X plus big Y. Oh, neat. That's an equation that's in exponential form. I see a number is equal to b raised to a power. Yeah, that's exactly what it means to be in exponential form. I can rewrite this in log form. B is the base, so B will continue to be the base, but it will now be a base in a log, and this will be inside the log. So the log base b, maybe I'll even write it right here. So the log base b of the stuff that's currently on the left-hand side, x times y, is equal to big X plus big Y. So, putting that down here, log base b of little x times little y is big X plus big Y. In some sense, that seems like it answers the question, but big X and big Y were artificial variables introduced for the sake of the problem. They shouldn't be part of the conclusion, if that makes sense. I only want a formula that involves little x and little y. But I know what big X and big Y are. Big X is the log base b of little x. Sorry, you can probably hear that little cat meowing, no, pawing. Log base b of little x plus log base b of little y. So, there's our approximating formula. Let's fill it in. Log base b of x times y is the same thing as the log with that base of little x plus the log with that base of little y. Nice. So there's the first of the main results that this particular lecture is going to cover. Let's use that result to achieve some things. So, let's start with this. Let's try to evaluate something that we couldn't evaluate normally. And on the one hand, you could bust out a calculator and compute the log base 3 of 2 and the log base 3 of 1.5 and then add them together. But if you do that, the machine will get a decimal approximation for the log base 3 of 2. It'll get a decimal approximation for the log base 3 of 1.5. When it adds them together, these decimal approximations may introduce some rounding errors. So let's see if we can do it by just thinking instead of by trying to use a machine. So I see right now that this is a logarithm plus a logarithm. Well, the rule that we just established says that a logarithm plus a logarithm can be written as a single logarithm of the product of the two things. So let's use that. That rule says, oh no, that the log of 2 plus the log of 3 is the same thing as the log with that same base. So log base 3 in this case of 2 multiplied by 1.5. Well, hey, that's exactly the log base 3 of 3. And, well, log base 3 of 3 is one of the few things that I do know how to compute without any help. Log base b of b is always equal to 1. So this totals up to just 1. So that illustrates that these logarithm laws can be used to simplify logarithmic expressions to something that's easier to work with. And one thing that will allow us to do will be to solve equations. Once you build up some algebra, you can use that algebra to solve equations. Let's do that. Let's try to solve the equation the log base 3 of x plus the log base 3 of x plus 8 is equal to 2. So again, I see a log plus a log. I can turn the left-hand side of this equation into a single log of a product. Cool. And there are two things that I can do now. This thing on the inside, I can distribute that. And I see a log on the left-hand side. So this is a logarithmic equation. I can rewrite it as an exponential equation, and that's a good idea because the stuff inside of the parentheses has all of the x's. So let's do that. So distributing to see what's in the middle, I'll get x squared plus 8x is equal to, and I'll move the base 3 to the other side. It'll still be a base, but now it'll be the base of an exponent. 3 squared. 3 squared happens to be 9. That's nice. So now this isn't a logarithmic or exponential equation. It's just a polynomial equation. It's quadratic. These things are easy to solve. I'll rewrite that as x squared plus 8x minus 9 equals 0. And there are a handful of different ways to solve this, right? You could solve it by factoring. it does factor. I've chosen these numbers carefully. You could solve it by using the quadratic formula. You could solve it by completing the square. Take a moment and use your favorite one of those. I'll proceed by using, oh goodness, how about completing the square? I'll complete the square. So to complete the square, what do you need to do? Well, I see x plus 8x, so I know that there should be an x squared plus 8x, rather, an x plus 4 quantity squared, because 4 is 8 divided by 2. But that will introduce a new plus 4 squared term. So I'll need to subtract 4 squared, which is 16, and I need to remember that there's a minus 9. So that becomes that. Moving everything that's not, moving the 16 and the 9 to the other side. 16 plus 9 is 25. I'll get x plus 4 quantity squared equals 25. So x plus 4 is plus or minus 5. Right? Undo a square with a square root introduces a plus or minus. So we'll subtract the 4 to the other side. We'll get x equals negative 4 minus 5 is negative 9, or negative 4 plus 5 is plus 1. So it looks like we're done. It looks like we have two solutions. But you know what? Let's do a quick check, make sure that they're both solutions. Let's try to plug them in. There's a reason that I'm doing this. Many times I don't check the solutions, but there's an important phenomenon that we're about to see. So let's check. X equals negative 9 and see what happens. Well, we'll get the log base 3 of negative 9 plus the log base 3 of negative 1, and this is supposed to be equal to 2. But we see a problem, don't we? I can't see a negative inside of a log. That is explicitly forbidden. Neither of these actually exist. So x equals negative 9 is not actually a solution. It's not even in the domain. So this in particular is not a solution. Let's also check x equals 1. Though maybe you see that it should wind up being just fine. It's still good practice to check. Let's plug in x equal to 1. So I'll wind up with log base 3. So I'm just reminding myself what the original equation was. Log base 3 of x. So log base 3 of 1 plus log base 3 of x plus 8. 1 plus 8 is 9. Let's expand that out. Hopefully this gives us 2. So at least I see that there's no issue with things being negative. This number actually exists. Log base 3 of 1 is 0, plus log base 3 of 9. Well, 9 is 3 squared. So what power do I need to raise 3 to in order to get 9? 2. So log base 3 of 9 is 2. Yeah, that's 2. That checks out. So let's explore why something went wrong. The thing that can possibly go wrong when you use these logarithm laws is you might accidentally make the domain bigger. I see log base 3 of x and log base 3 of x plus 8 here. So notice if that's negative and that's negative, if both of these things are negative, I'm adding together two things, neither of which exist. But this thing down here, a negative times a negative will be positive. So sometimes the thing that you get after you use the log law, this second thing, well, in this case, it definitely has a bigger domain. Than the original expression. So there might be some fake solutions. So once you find solutions using these techniques, you should make sure that they're actually solutions by seeing if they're in the domain. That's the point. Okay, so let's use another log. Let's derive another log law. So multiplication inside of a logarithm becomes addition. Division is like the opposite of multiplication, so it should somehow become the opposite of addition, which I guess should be subtraction? So maybe, this is just a guess, maybe the log base b of x divided by y should be the log base b of x minus the log base b of y. Well, let's find out. Let's actually go through the proof of this. So it'll be super similar to what we just did for products, so maybe I'll encourage you to hit pause, figure out the proof on your own, and then watch what I'm about to say at double speed. Okay, break. Good. I hope it went well. So let's figure it out. The log base b of x, we'll give it a name. In order to avoid that nonsense about crossing the x and y, maybe I'll call it the log base b of x s and the log base b of y t. Now I have variables that even in my poor penmanship look definitely different. Those are both logarithmic equations, right? I see log base b of x is equal to s, so that's a log is equal to a number. I can rewrite that in exponential form as x is equal to b to the power s. Log base b of y is equal to t. I can rewrite that as y is equal to b to the power t. Now I know what x and y are. Well, I have some things that are equal to x and y, so I can take x divided by y and write it out in terms of s and t. X divided by y will be, x is b to the s, divided by y is b to the t. But I have exponential laws. B to the s divided by b to the t is b to the s minus t. Ah, so just like last time, now I see an exponential equation. I see that this is equal to this. That's an exponential equation. So writing that, maybe just for the sake of emphasis, I see that x divided by y equals b to the s minus t. Let's put that in log form. We'll get log base b of the thing that's on the left-hand side, x divided by y, is equal to s minus t. So just for convenience, I'll put that right here. Log base b of x divided by y is equal to s minus t. Oh, wait, but I know what s and t are. There's s. S is the log base b of x. T is the log base b of y. So making that substitution, this is equal to log base b of x minus y. Nope. Log base b of x minus log base b of y. So the log base b of x divided by y is the log base b of x minus the log base b of y. Now, what will I do? I'll go back to that first page. And you should do this too. You can do it faster than I can. The second result of today is the log base b of x divided by y is equal to the log base b of x minus the log base b of y. And for emphasis, the reason that that is true is because b to the x divided by b to the y is b to the x minus y. Nice. So, now, to emphasize parallel structure, let's use this fact to do some similar simplification. Let's compute log base 5 of 15 minus log base 5 of 3. It won't even be that hard. log base 5 of 15 minus log base 5 of 3, I see a log minus a log. I know that a log minus a log is the same as a single log of a quotient. So this is the same thing as the log, same base, base 5, of 15 divided by 3. Oh, but 15 divided by 3 is just 5. That's the log base 5 of 5. So that's just 1. Similarly, we can use the same simplification trick to solve equations. Let's try to solve this equation. Let's try to solve log base 2 of x plus 2 minus log base 2 of x plus 1 is equal to 3. Well, let's do it. So again, I see a log minus a log, so I can rewrite it as a single log of a quotient. I can rewrite this as the log base 2 of x plus 2 divided by x plus 1. That's supposed to be equal to 3. So now I see a single log of a thing is equal to 3. That's an equation in log form. I can rewrite it in exponential form as x plus 2 divided by x plus 1 is equal to the base is 2 raised to the power 3, but 2 to the 3, I know what that is. That's 8. So x plus 2 divided by x plus 1 is equal to 8. Now, because I've seen you do it enough times on homework, I'll go ahead and say that you can't do something silly like cancel these two x's. Just because you see an x in the top and the bottom of a fraction doesn't mean they cancel. You can only do that if everything in the top is multiplied by x and everything in the bottom is multiplied by x. That's not the case here. With that out of the way, though, how do you solve a rational equation like this? Well, the first thing you should do is clear the denominator. Let's see if it helps. So to clear the denominator, that means I want to multiply both sides by x plus 1. If you like, this is also sometimes done under the name cross-multiplying. I'll cross-multiply by x plus 1. So what will I get? I'll get x plus 2 is equal to 8 multiplied by x plus 1. Those parentheses matter a lot. I need all of x plus 1 to be multiplied by 8. But now that I have those parentheses there, I want to get rid of them. How do you get rid of them? You distribute. So I now have x plus 2 is equal to 8x plus 8. That's a linear equation. This is easy to solve. All I should do is put all the x's on one side, everything else on the other side. Then I guess I need to do some division. So let's see. I'll, subtract 8 from both sides to get the 8 over to the other side, and I guess I should subtract x from both sides. And what will I wind up with? Well, x minus x is 0, that's why I subtracted the x. 2 minus 8 is negative 6, is equal to 8x minus x leaves me with 7 x's on the right-hand side. So negative 6 over 7 equals x. So there's an answer, but just as before, there's this issue where I don't like the shape of that box. Just as in the last time I solved, you should be a little bit novice whenever you see things that might involve negatives showing up in logs, because I know that I can't literally plug a negative into a logarithm. I can't see a negative as the only thing in a log. So let's check whether this is actually in the domain. So I'll write it out in more words than I would often do to explore all the details. So let's see, for log base 2 of x plus 2 to make sense, I need x plus 2 bigger than 0, so I need x to be bigger than negative 2. Oh, well, let's see. Negative 6 over 7 is bigger than negative 2. Negative 6 over 7 is bigger than negative 2. I'm fine. Oh, rather, there's no problem yet. There's another log, though. Let's check log base 2 of x plus 1. For log base 2 of x plus 1 to make sense, I need x to be bigger than negative 1. So I need x plus 1 to be bigger than 0. Solve that for x. X is bigger than negative 1. Oh, but let's see. Negative 1 is negative 7 over 7. Yeah, that's less than negative 6 over 7. Negative 6 over 7 would be to the right. So negative 6 over 7 is in the domain. And we conclude that x equals negative 6 over 7 solves the equation. Good. So there's one last rule that I want to do in this half of the lecture, and that's thinking about exponentiation. So logs denote multiplication to addition, and multiplication is like souped up addition. Similarly, exponentiation is like souped up multiplication. It's like iterated multiplication. So it should get demoted to just multiplication. That is, I think that the log base b of x raised to the power y should be equal to y multiplied by the log base b of x. Let's go through the argument. So, one thing that I'll say is, well, it looks like this y is going to stay a y. There's not going to be a log that shows up around the y, so I'll leave the y alone. The x, on the other hand, I'll give log base b of x a name. I'll call log base b of x no, I'll just call it a. No need to be fancy. Again, that just giving something a name is really powerful because it lets you do algebra to that equation. I can rewrite that in exponential form to get x is equal to b to the power big A. Well, now let's take x to the power y, that is to say, this bit. Let's substitute, simplify, and rewrite it in log form. So step 1, substitute. X is equal to b to the a, and then I raise all that to the y. So if you like, what have I done? I've taken this x, which now I've written in red, and I've replaced it with this, because I know it's equal to it. So there's the substitution. Now we simplify. B to the a to the y. There's an exponential law for that. That's b to the a times y. So now I see the following. I'll color code a little bit. I see x to the y is equal to b raised to the, I think that I'll use this color, b to the a times y. That's something that's in exponential form, right? I see something complicated, but it's a number, is equal to a base to a power. That's an exponential form. I can rewrite it in log form as the log base b of x raised to the y is equal to a times y. Oh, but what is a? I know what a is. A is the log base b of x. So this is equal to log base b of x times, no, that's the wrong color. I'm done with the color coding now. That's equal to the log base b of x, because that's what a is, times y. Oh, neat. That's exactly the formula we claimed. The claim was log base b of x to the y is equal to y times the log base b of x. Log base b of x to the y is equal to log base b of x times y. Doesn't matter if you multiply before or after. Cool. So there's the the third important formula on that front page. So the log base b of x to the y is equal to y times the log base b of x. So whenever you see an exponent inside of a logarithm, you can pull it out front as a multiple. And the reason it's true is because the exponential of an exponential is the exponential of a product. Nice. So I'm quite nearly done with what I want to say in this video. There's basically just one thing left to do. Let's put all this together and solve a complicated logarithmic equation. And, well, here, let's do it. So here's an equation. 2 times the log base 5 of x plus 1 minus the log base 5 of x minus 1 is equal to 2. So I'll do the manipulations one step at a time. So I see here 2 times a logarithm. Oh, so that's a number multiplied by a log. A number multiplied by a log, I can take that number and put it in the exponent. So that will give me log base 5 of x plus 1 quantity squared minus the log base 5 of x minus 1 equals 2. But now what do I see? I see 2 logs being subtracted. The difference between 2 logs is the log of the quotient. So maybe for emphasis, I'll color code that in blue on the next step. This will give me the log base b of x plus 1 quantity squared divided by, in blue, x minus 1, close parentheses, equals 2. This is nice because this is now an equation which is in log form. And it's in log form, and inside of the logarithm are all of the variables. Everything we want to solve for is inside of the parentheses, so rewriting in exponential form will make our life easier. Oh, all of those b's are 5s, aren't they? So let's rewrite that in exponential form. I'll get x plus 1 squared divided by x minus 1 is equal to 5 to the power 2, also known as 25. And, well, the manipulation maybe will get harder because the numbers are bigger, but that's okay. So what will I do? So this is a rational equation. I see a rational function is equal to 25. So I should clear the denominator. I should move the x minus 1 over to the other side. Doing that will give me x plus 1 quantity squared is equal to 25 times x minus 1. And I think what I'll do is I'll go ahead and FOIL out the right-hand side, giving me x squared plus 2x plus 1 on the right-hand side is equal to, and I'll distribute on the left-hand side, 25x minus 25. And now let's solve for x. X squared, so I guess I should subtract this over to the other side. So I'll see 2x minus 25x, that leaves me with negative 23 x's. I'll need to add 25 to the other side. So plus 1 plus 25 is plus 26 equals 0. I'll get x equal to quadratic formula, I think, is the most reasonable thing here. 23 plus or minus the square root of b squared minus 4 times a is 1 times c is 26 all over 2a. And this looks like a complicated thing. I wouldn't want to, I won't do any more simplification by hand. So what I will do, though, is I'll go ahead and get estimates for both of those. And, well, the way that I will do that is I will pull up the thing that I use to do all of my just computations. There, that's a good spot for it. Wolfram Alpha is what I will use. And you know what? I won't make you watch me type in an expression because that will take too long. So I will pause the recording and I'll come back. Okay, I'm back. So it looks like the plus branch results in something that's around 21.8. And again, I'll be right back. And the minus branch gives me something that's around 1.2. So I see two solutions. And let's take a moment and decide if these solutions are actually in the domain. So let's do a quick domain check. Yeah, I've got space off to the side. Note, I don't need this anymore. So let's do this domain check. So let's see, I need x plus 1 to make, log of x plus 1 to make sense, and I need the log of x minus 1 to make sense. So I'll need x plus 1 to be bigger than 0, and I'll need x minus 1 to be bigger than 0. Well, if x minus 1 is bigger than 0, then x plus 1 will be bigger than 0 automatically. So this is somehow the strongest condition. That's the only one I need to check. So solving that, you see that x has to be bigger than 1. So the domain of consideration is the interval from 1 to infinity. Oh, son of a diddly, I did write those down. All right, one of them was like 22-ish, and the other one was 1.9-ish. So now let's see, are both of these options in the domain of consideration? I think they are. So x equals 22 and x equals 1.9 are actually solutions. All right, I went back and I checked the tape. It wasn't 1.9, it was 1.2. But it stands. Both of those are in the domain, so those two things are both solutions. Nice. So, the next thing that's in this particular set of notes is some stuff about the change of basis formula. And the reason that it appeared at this point in these notes is it's natural enough to put here, and there's time at the end of these notes if I have a 50-minute time slot, and I talk a little bit faster than I have been. But I'm not bound by that, so I'm going to stop this recording, I'm going to post it, and then I'll record another video in which I'll explore the change of basis formula. See you then.